class. Today's lecture will be on covalent bonding, topic 4, section 2. First question we need to answer is, how are covalent bonds formed? We learned previously that two atoms with different electronegativities, like a metal and a nonmetal, they will bond when the less electronegative metal transfers its electron to the more electronegative nonmetal, forming ions. Those two ions then will be electrostatically attracted to each other, and we call this an ionic bond. And the driving force between the transfer of electrons is this formation of an octet, the stable noble gas configuration. Well, if I have two nonmetals which have similar electronegativities because they're on the right-hand side of the periodic table, there will be no transferring of electrons between those elements because they have equal electronegativities. However, we can see that they can share electrons, and through sharing electrons, they achieve an octet. We also see that that bond is as an electrostatic attraction not between oppositely charged ions, but instead between the protons of one atom and the shared electrons. So the nuclei of both atoms are attracted to the shared electrons, and that makes the bond, and these are both very strong bonds. So how do we model covalent bonding? We are going to use something called Lewis dot diagrams to model covalent bonding. The Lewis dot diagram is simply the symbol of the element, and if you can imagine that there's a box around that element, on each side we will represent the valence electrons as dots. And as you see with the noble gases, there are 4 pairs of these dots on each side of the symbol. So that would be the octet that we are trying to achieve. So how do we model actual bonding? Well, we take the Lewis diagram and we create what's called a Lewis structure. And this Lewis structure shows us how each of the elements has an octet, and what electrons are going to be shared and which electrons aren't going to be shared. So you can see that fluorine has 7 valence electrons, and if we have a fluorine molecule, F2, it's one of our diatomics, we can see when the two fluorines come together, they can share 2 electrons, and then if you circle one fluorine and count how many electrons are around it, you'll see that there are 8 around both fluorines. So in diagram A, in order to see the shared electrons, one fluorine has X's for its valence electrons and the other has dots. But in diagram B, you'll see every electron, the shared and the unshared pairs, shown as dots, the same diagram. And C is actually the way that we're going to draw Lewis structures. We convert the 2 dots that are shared into a line to show a bond, and then all of the other electrons, we're going to call them non-bonding electron pairs. And these become very important in our next section 3, in helping us determine what shape this molecule will have. Another example is the O2 molecule. In this case, if you look, oxygen has 6 valence electrons, and so if we share 2, we'll see that one oxygen will end up with an octet on the right, but the other one on the left has just 6. So what we have to do is we have to take that bottom pair of electrons and we have to share that as well. And so instead of sharing 2 electrons, these 2 oxygens are going to share 8 electrons, not 8, 4 electrons, and we'll call that a double bond. And so if you draw a circle around each oxygen in C, you'll see that they share 4 electrons in the double bond, plus they have 4 non-bonding electron pairs, giving each oxygen an octet. So this would be a Lewis structure for a double bond. Now let's look at a Lewis structure for 2 different elements coming together. Hydrogen with its 1 valence electron, fluorine with its 7 valence electrons, coming together to form hydrogen fluoride. The fluorine now has 8 valence electrons, and hydrogen has its 2 valence electrons, the noble gas configuration of helium. And so I convert the 2 dots representing the electrons that are shared into a line, and this would be the Lewis structure for hydrogen fluoride. So now let's think about, well, we can see that 2 atoms won't always just bond once, but they might bond twice, and actually a triple bond is the highest number of bonds that you can have between 2 atoms, so that's 6 shared electrons. So how can we relate the number of bonds to the length and the strength of that bond? Well, let's look and first determine how a length between two atoms is determined. Well, we know that the two nuclei are going to repel each other, and the nuclei and the electrons will attract each other. So if you look at this diagram, we have the red line, which is showing the change in energy with the change in distance between the two atoms. So as the atoms get closer, the energy becomes more negative, and negative energy is energy that's released. And we always say that the most stable state releases the most energy. So if you look at the trough, the very bottom part of that graph, you'll see that diagram 3 shows the ideal bond length, the length at which the repulsions are minimum and the attraction is maximum. And we know that because that releases the most amount of energy. As soon as the nuclei get too close together, like in 4, we see that there's less energy released. So that's a less stable state. So the bond will find the perfect distance which balances repulsions and attractions. Another way of looking at it is we have the way too far apart, not enough attraction, and then we have the way too close, which is too much repulsion, and then we have just right, like Goldilocks and the 3 bears. All right, so what does this bond length have to do with multiple bonds? Well, if you think about it, multiple bonds have more electrons that are shared, and that makes that part more negative. And so more negative means that there's going to be a greater force of attraction. And so we see that a carbon-carbon, if you see in the upper left-hand corner, the carbon-carbon bond is shorter. So its perfect distance that maximizes attractions and repulsions is much closer than a carbon-carbon single bond, and that has to do with the density of electrons that are shared, and then you have a greater amount of attraction and a shorter distance. So we can summarize that with multiple bonds, bond length is shortest with the triple bond and greatest with the single bond. So single bonds are greater in length than double bonds, or greater in length than triple bonds. Now let's look at energy. So if we look at carbon-carbon single bond, we see that these bond enthalpies is the amount of energy I need to put in to break the bond. So that basically is equal to the amount of energy that came out, that was released when I made the bond. So if I look at the carbon-carbon single bond, that has 348 kilojoules per mole are necessary to break that bond. But if I look at the carbon-carbon triple bond, it's 839. So that bond, it has a lot more energy because of that high density of electrons that's creating a great force of attraction between the two nuclei. So it takes a lot more energy to overcome that attraction. So for bond strength, we know that a triple bond is much greater in strength, and the double bond is much greater in strength than the single bond. Now let's compare ionic and covalent bonds now that we've learned a little bit about them. An ionic bond is formed between a metal and a nonmetal, a covalent between two nonmetals. Ionic bonds happen when we transfer electrons. Remember, this is redox. The way we're going to remember what reduction means and what oxidation means is by using a mnemonic GRAL. Gaining electrons means you're reduced, and losing electrons means you're oxidized. In covalent bonds, they're sharing their electrons, and these bonds are both electrostatic attractions, but with ionic bonds, it's an electrostatic attraction between ions. In covalent bonds, it's an electrostatic attraction between shared electrons and nuclei of the two atoms. Remember, ionic bonds form a lattice structure. Covalent bonds form individual molecules, and therefore I can draw a Lewis structure. However, with an ionic substance, can I draw a Lewis structure? No, because it forms this huge crystal of alternating negative and positive charges. So remember, the word molecule is always about covalent substances. We learned from lab that ionic substances, like copper sulfate, have high melting points, where covalent substances, like paraffin, have lower melting points. We haven't observed this yet, actually we will in one of our labs, that ionic substances have low volatility, and that is the tendency to change state from liquid to gas at room temperature, where the covalent substances have a much higher volatility. And the last physical property we'll look at is conductivity. Ionic substances are made of charged particles. So if those charged particles are free to move, then it will conduct electricity. So the only way that the ions are free to move is if either you dissolve the ionic substance in water, which pulls the ionic bond apart, or if you melt the substance. In that case, the ions will be moving, and so ionic substances will conduct electricity if they're dissolved aqueous or if they're in a liquid state. In a solid state, the lattice structure won't allow the ions to move and they can't conduct electricity. And covalent substances are not charged and do not conduct electricity. All right, the last thing we're going to look at today in our lecture is how can we characterize a bond using electronegativity. So this is our electronegativity chart. Notice that green means low electronegativity and yellow means high, and we know the trend as we move from left to right across the periodic table. For the most part, that's a trend. We see an increase in electronegativity. So we know that we are going to learn right now that there are two different types of covalent bonds. There is the non-polar covalent bond, which means that the two atoms in the covalent bond have equal electronegativity. So imagine people of equal strength in a tug of war. One element cannot pull the electrons toward themselves. They're going to be really sharing them truly equally. And that would be between two hydrogens. They both have the same electronegativity, so they're going to share those two electrons equally. However, if you look at a bond between hydrogen and chlorine, chlorine has an electronegativity of 3, which is 0.9 greater than hydrogen's electronegativity of 2.1. They're not going to share, even though they're still sharing, they're not going to share the electrons equally. The electrons will spend more time around chlorine. So we're going to call this a polar covalent bond because poles develop. One side of the molecule will be negative and the other side, one side of the bond will be negative and the other side of the bond will be positive. So here we look at another example of non-polar covalent bonding, Cl2. We drew that early. Oh no, yeah, we did. So the way we can characterize a bond as non-polar covalent is by subtracting the two electronegativities. And if we get a number equal to 0, then we know we have a non-polar covalent bond. In polar covalent bonding, if we subtract the electronegativities and we get a difference between 0.0 and 1.8, then I know I have a polar covalent bond. And so we have hydrogen iodide and then we have water. The difference between hydrogen and iodide is 0.4, so we're going to have the hydrogen will have the positive pole and the iodide will have the negative pole, and we show that with the lowercase Greek letter delta, meaning change in. And then the same thing with water. The oxygen end, which is 3.5 electronegativity, will have the negative pole, and the hydrogen end will have the positive pole. The difference in the electronegativities is 1.4, and that way, if I subtract the electronegativities, I can characterize the bond as a polar covalent bond. So if we look at what's happening with the electron densities in a pure covalent bond, we see the electron density is equally distributed around the two atoms, and that's happening between electronegativities differences of 0 to 0.4. Now with a polar covalent bond, it's still a covalent bond, they're still sharing electrons, however the electron density is going to be greater around one atom than the other, and you can see here in gold that atom is more electronegative, and so we're sharing the electrons unequally, and that's called a polar covalent bond. This diagram shows the 2.0 as being the limit, but your textbook talks about it as 1.8. So if you have an electronegativity difference of 1.8 between 0.4 and 1.8, then that's going to be a polar covalent bond. Greater than 1.8 means that the electrons going to be transferred. There's no more sharing. The electron will move from the less electronegative atom to the more electronegative atom. So this is a guideline for how we can characterize a bond as either ionic, polar covalent, or pure covalent. So this is the guidelines that we're going to use from your book. An ionic bond has a difference, so I subtract the electronegativities of the two atoms and it's greater than 1.8. A pure covalent substance has an electronegativity difference of 0, and a polar covalent substance, and covalent there is spelled wrong, is between 0 and 1.8. And chi subscript P is going to be our symbol for difference in electronegativity.